Okay, so before we do the chain rule for functions of more than one variable, let's look at calculus 1. So you guys know the chain rule, right? You know, in calculus 1, when you use the chain rule, usually it's for what we call a composite function. So for example, if you were given, say, f of x equals, I'll make something up, x cubed plus 7 to the 99th power, for example, you would have to use the chain rule to take the derivative. So when they teach you the chain rule in calculus 1, what they like to do is they use u, not really u substitution, but you can kind of think of it. So they usually call the inside function u, and u is a function of x, like so. So what they do is you've got f of x is your parent function, but really your f is a function of u, and then u is a function of x. So they do that. So what they make you do when you take the derivative, so what is the derivative of f with respect to x, even though x is way down here on the food chain, they use that you have the chain rule. So first you take the derivative of f with respect to u, and so you go down this using this schematic. You first do df du, and then you multiply that by du dx. Have you guys seen this version of the chain rule when you took calculus 1?
I don't remember that.
Okay, so the way you would do it, so this function here, I'll just do it on this example. If you were to say this is f of u, where u is the stuff inside parentheses, it looks like u to the 99th power, like that. So df du would be using what we call the power rule, is 99 u to the 98th power, yes?
Yes.
Then du dx, if u is equal to x cubed plus 7, the derivative of x cubed plus 7 is 3x squared, yeah? So when you take all of this and you take the chain rule here, df dx is df du, which is 99 u to the 98 power, times 3x squared, that's the du dx factor. But then you replace u with what it was, because you said up here that u was the quantity x cubed plus 7, so you put it back in. And then your final answer would be this, although you probably clean it up a little bit by multiplying the 99 with the 3 and so on. But the basic idea here is you've got this composite function, and so you take the derivative of f with respect to u, and then you take the derivative of u with respect to x, and they call it the chain rule, right? So you kind of chain your derivatives together. So this whole idea is going to be similar to what we're doing in Calc 3, but a little bit higher level. So I'm done with my review for Calc 1. Hopefully you got something from that, even if you didn't cover the chain rule in the way that I've described it. That's unfortunate because the way I'm describing it here is the classic way that almost every Calculus 1 textbook goes over when they do the chain rule for a function of one variable. Okay, so now let's do chain rule for a function of several variables. So there's two cases that you have to be apprised of, and you have to know how to do both cases, even on the exams and quizzes. So case 1 is where w is going to be a function of x and y. Write this down. W is a function of x and y, where x and y themselves are functions of a single variable t. X and y are functions of a single, this is the key here, single variable, and we'll just call that variable t. It could be some other letter, but we'll just use t. That's very common. The second case we're going to look at today is you still have w as a function of x and y, where This is going to be the difference here. This is a little bit more complicated than the first case. X and Y themselves are functions of two variables. And it might even be more than two. I'm just being kind of simplistic here. Are functions of two, and I'll put just in parentheses, or more, it doesn't have to be two, variables, say U and V. Different letters they're using. But it doesn't have to be U and V. They could pick some weird letters like R and Q, you know. We're just putting dummy variables in there. Okay, so we're going to do both of those cases today. So we're going to start with case one. Here we go. Case one. This is where the chain rule where you have one independent variable. So you have W. W is a function of X and Y. And it's a differentiable function of X and Y. That's key. Now, if X and Y are themselves functions of a single variable T, so X looks like G of T and Y looks like H of T, where G and H are also differentiable functions of T now, then you can say that W is a function of T. So you sort of have like a transitive property going on here. So what is dW dt? The derivative of W with respect to T. So this is the chain rule. Here we go. You're going to take the partial of W. Remember the notation for partial derivatives. The letter D has a curvy stem, not a straight up stem, not a straight stem. That's how you denote a partial. The partial of W with respect to X times, now you're going to use a straight stem D because you have a single function of a single variable. So the D here, dx dt, these D's are straight stem D's. And yes, it matters. I'm going to dock you points if you get these wrong, because this is like key. We're part of the understanding too, is showing me you understand this notation. There you go. There's the chain rule. Oh my God. So here's the weird part. It just defined the derivative of W with respect to T, and T usually represents time, but it doesn't have to. You have to come up with four different derivatives, dw dx, dx dt, dw dy, and dy dt, and put them all together according to this formula. Yeah. Now I'm going to show you a schematic. I'm actually going to show you two schematics. I'm going to show you the schematic that your textbook uses and most textbooks use. And then I'm going to show you my preferred version of that schematic according to my mentor, Dr. Arnie Vallone of blessed memory. So here's the schematic you'll see in most textbooks. So here's what Briggs will have. You've got W up at the top, but W is a function of X and Y. Okay. But X is a function of T, and Y is also a function of T. And we're done. There's the schematic for the function. Now, when you're doing the chain rule along these branches, just to help you get the chain rule, this branch would be the partial of W with respect to X. And then along this branch, you would take the derivative straight stem because you only have a single variable here of time T, dx dt. And then along this branch, you take the partial of W with respect to Y. And along this branch, dw dy dt. And hopefully you'll see that this schematic kind of helps you get all the four different derivatives that you need in this formula if you follow the branches on your schematic. So I'm going to show you the schematic that I prefer. It's similar, but I'll tell you why I think this is superior. So I still start at the top. I've got W, and W is a function of two variables, X and Y. But X and Y are functions of time T, but not a different time T. The reason why I don't like the Briggs schematic too much, it looks like this T over here is different from the T for the Y, but they're really the same T. And so a better superior diagram is to show you that T is just one variable who's driving the whole bus, that X and Y are functions of the same T. It's not a different T. So this schematic that I have here kind of shows you better what the relationships are. And you still can go down your branches here and show which derivatives have to be taken in order to be corresponding to your formula up here for the chain rule. Okay? So this shows you that you have one independent variable who's driving the bus, who's driving the whole situation here. When he changes, he makes changes in everybody because everybody is dependent on him. So now let's do some examples of the chain rule. Okay, here is a function w who's a function of x's and y's, x squared y minus y squared. But x and y themselves are functions of an independent variable t, one independent, where x is given by sine t, y is given by e to the t. We're going to find the derivative of w with respect to time t at time t equals 0 using two different methods. What? Why do we have to use two different methods? You'll see. Method one, we actually are going to use the chain rule that we just learned for functions of two variables. So we are going to use this big old formula here. And we're going to have to get four separate derivatives here and put it all together. So by the theorem here, the theorem says that dw dt is equal to the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt. Fine. Now let's get these four partials separately and then we'll put it all together. So let's get the partial of w with respect to x. We went over partial differentiation in the last lecture. So take a look here. Remember when you're doing the partial with respect to x, you put on your special set of glasses and temporarily all the y's look like they're a constant, like a 2 or something, and you differentiate with respect to x. So the first term, the derivative of x squared y with respect to x is 2xy. And the derivative of the second term minus y squared is going to be 0 with respect to x, because y looks like a constant. Now, let's go get the other partial, dw dy. That means you put on your other set of glasses, because since you're going to differentiate with respect to y, x is going to be held constant. So the derivative of the first term, x squared y, with respect to y, is x squared. And then the derivative of minus y squared with respect to y is negative 2y, or minus 2y. Got to get two more. We need dx dt, and we're going to still need dy dt, and then we'll put it all together. So dx dt, the derivative of sine t with respect to t is cos t, and the derivative of y, which is e to the t, is simply e to the t. Now we're going to put it together. You're not going to like this because this answer will be unacceptable. We have to change it up. What? We did all this hard work for nothing? No, just wait. So you're going to go, all right, I'm going to follow this theorem and put it all together. So we have dw dx first, that's 2xy, times dx dt, that's cos t, plus dw dy, x squared minus 2y, times dy dt. That's wrong. Oh, wait a minute. You made it, you do all this hard work and now you're telling me it's wrong? Well, here's the thing. Because you're giving the derivative of w with respect to time t, the only variable I should see in that result is t. But I'm looking at it now. I've got alphabet soup here. I got x's and y's and t's. Not good. Oh, well, what do? You just start substituting. So you need to rewrite it. Well, what do you mean? Everywhere you see x's, you have to acknowledge the fact that x is the same as sine t. And so you do a substitution, and y is e to the t. So 2xy becomes 2 times sine of t, e to the t, and then you multiply that with your cos t. Plus, I'm running out of room here, but x squared minus 2y becomes sine squared t minus 2e to the t, and you multiply that with e to the t. And I can clean this up a little bit to make it look a little prettier. I'll do that down here. So the first term, it looks better if you put your exponentials in front of your trig functions. And I'll distribute this e to the t over the difference. So I'll have e to the t sine squared t minus 2e to the 2t. So there's the derivative of w with respect to time. And now I'll evaluate that at time t equals 0. So now we're just going to substitute 0 in place of time. And you know the drill. Since sine of 0 is 0, the first two terms are basically going to be zeroed out, and only the last term is going to contribute. So -2 is the final answer. Okay? So that's the chain rule in action. Now, what about method 2? Method 2 is, I like to think of it as the criminal mind. This is where you don't even have to use the chain rule at all. You circumvent it. Well, what do you mean? Well, since they're telling you that W is a function of X and Y, and they're giving you the X and the Y, you could just rewrite the W and go, oh, you know what? I don't need W I don't have to worry about finding the partials of X and Y with, all these things, W with respect to X and Y. So if you rewrite the W using the given functions for X and Y, let's see, W is going to be X squared, that's sine squared T, times Y, that's e to the T, minus Y squared. So W is really e to the T sine squared T minus e to the 2T. So now that W is just straight, it's a function of T right off the bat. So now we don't even need the chain rule to get dW dt. This is like a calculus 1 problem. It's like, oh, I have W as a function of T straight away. So now dW dt, I just use my knowledge of functions of a single variable. So I am going to have to use the product rule to find the derivative of e to the T sine squared of T. So let's do that. The derivative of e to the T is e to the T. Multiply that with sine squared. Plus the derivative of sine squared is 2 sine t cos t, and then multiply that by e to the t, and then minus, and then the derivative of the last term is 2e to the 2t. And I hope you can agree that this is basically the same as this, right? They're equivalent. Now, if you're thinking to yourself, wow, I think it's just much better if I just circumvent the whole kit and caboodle and don't bother with the chain rule. Well, that might be nice, except for I usually give you problems where that's not possible. I tend to avoid this kind of situation on quizzes and exams. So don't even think about it. I'll give you an example right now where you won't be able to circumvent that. So here's an application of the chain rule. Now, for those of you who remember your Calc 1 days, one of the things you might remember is related rates. So do you recall related rates at all from Calculus 1? Well, maybe not. Well, this is the analog here in Calculus 3, related rates is this stuff here. So for example 2, let's say you have a rectangular block of ice. So it's got a width, a length, and a height. And let's say it's melting. But when the length is exactly 9 feet, the width is 8 feet, and the height is 2 feet, the variables are changing such that the length, the rate of change of length, dl dt with respect to time, is -1 foot per hour, because the block of ice is melting, so everything is shrinking. And the rate of change of width with respect to time is -2 feet per hour. Ouch. And the rate of change of the height with respect to time is -1/3 foot per hour. So the big question is, what's the rate of change in the volume? So they want to know, what is the rate of change of volume with respect to time t? That's the question. So folks, you're going to have to use the chain rule. You have no choice. Too bad. Why? Well, if I draw a little situation here, this might help you. Here's volume. Volume is a function of 3 variables, because we've got width, length, and time in no particular order. So volume is equal to length times width times height. So length times width times height. And all 3 of those variables are functions of time. And I'm going to use my diagram because it's the same time t driving the bus. So how are you going to apply the chain rule? We're using my little schematic, my little diagram. I know I'm going to have to find the partial of v with respect to L and multiply that by dl dt. plus, then I'm going to have to find the partial of the volume with respect to the width and multiply that by dw dt. And then finally, I'm going to have to find the partial of the volume with respect to the height, h, and multiply that by dh dt. So the chain rule is going to look like, when I'm applying the theorem now, but this is a function of 3 variables, so you got to extend the theorem a little bit. dv dt is going to be the partial of v with respect to L times dl dt plus the partial of v with respect to w times dw dt plus the partial of v with respect to h times dh dt. Well, my computer is slowing down. I wonder what that means.
Is that d for dt?
Hang on a quick second while I close out some tabs. So, which one there?
That's looking at the diamond, the right bottom, right?
This is a T right here.
Okay.
And then this here says dH dt. Does that help?
Yeah, that does help. Sorry.
dH dt. dH dt. And so I'm just putting it all together here in this big old thing. So how many derivatives total do we need just to get dv dt? Count them.
6.
6. Oh my God. Yeah. Yeah. And here's the thing, you're not going to be able to circumvent anything. Now, there's good news here, because you actually don't have to find dLdt, dWt, and dHdt. Those were given to you. What do you mean? Well, dLdt was -1 foot per hour. It's given. And the changing width with respect to time was -2 feet per hour. And the height was changing at a rate of -1/3 foot per hour. So those are given. So you just have to go get the partials of volume V with respect to L, W, and H. Let's do that in order here. Here we go. Knowing that the volume is this function, L times W times H, what is the partial of that with respect to L? So we're getting dV dL right now. So you're going to have to hold W and H constant and differentiate with respect to L. What are you going to get?
WH?
Yes. Plus, now you're going to need to get dVdW. Somebody besides Kimberly. I'm going to just start calling on people, okay? Let's see. Lizbeth, what do you think is dV dW, the partial of V volume with respect to width? You can talk to me in the chat box if you want. Elizabeth, are you there?
Times height.
Say that one more time.
Length times height.
Yes, you are correct. Thank you, Elizabeth. That's awesome. Okay, plus, and now somebody is going to tell me what is the derivative of volume with respect to height. This is another partial we need to get here.
L times W.
Say again.
L times W.
L times W. I think that sounds right. Okay. L times W. So those are the partials of the volume. Okay, now what? Well, now you can plug in some actual numbers. Well, what do you mean? Well, they gave you the snapshot moment of what the length and the width and the height are at the moment they want you to find this overall rate of change of volume. So you just plug that in. They said the length is 9 feet. So everywhere I see L's, I'm going to put a 9 here, 9 feet. There's a 9. And the width is 8 feet. So the W's get 8 feet. And then the height is 2 feet. Okay, 2 feet. So I have these feet here. Trying to put in my units. Feet. Height is 2 feet. And this is going to be feet squared here. So when you get out your calculator and you multiply all this out, you're going to get what? You're going to get like -16, and this is feet cubed per hour, plus -36 feet cubed per hour. And then finally 9 times 8 times -1/3. Oof, what the heck? 72 over 3, we'll figure that out in a minute, feet cubed per hour. And then you add all that together, and I get -76 feet cubed per hour. So this is the rate of change of volume with respect to time. So the block of ice is shrinking, the volume is shrinking -76 feet cubed per hour. And we're done. Questions?
So is that just the notation?
Yeah.
The F cubed H?
Yeah, well, F cubed is feet cubed. So if you prefer, you could put cubic feet there instead. -76 cubic feet per hour. Your choice.
Okay, just making sure.
But you better acknowledge the fact that it's feet cubed or cubic feet per hour. If you tell me feet squared per hour, you are sadly mistaken, because volume is cubic feet. Yeah, right. Feet cubed. So the rate of change of volume is going to be feet cubed per whatever your time units are. In this case, it's hours, but it could be minutes or seconds or days or whatever they decide the unit of time is for that particular problem.
Okay.
Now, this next problem, letter B, same block of ice, but surface area instead of volume. Now, I gave this on a quiz a couple years back, and I didn't do it in lecture. I did the volume change only. And I just said, oh, the students will be able to figure out, the rate of change of surface area. They know surface area of a rectangular box. And half the class started crying and shrieking, and and they were really upset. And to avoid that, I decided, well, maybe I overestimated the students' knowledge and they don't know surface area of a rectangular box. That's unfortunate. So let's do the problem. So same rectangular box, you've got the width, you've got the length, you've got the height, but instead of figuring out the rate of change of volume, let's get the rate of change of surface area of this melting box. So in order to do this problem, you need to give me the surface area. If you don't know this is where the students just cried. You should know how to find the surface area of a rectangular box. So you've got, the surface, say, of the front face would be W times H, but there's two of those faces. You got to account for the back side. So that's going to be 2WH. And you do the same for all the other faces. You're going to have 2LH plus 2WL. So this is S is a function, if you were drawing a schematic here, surface area is also a function of L, W, and H. And L, W, and H are still functions of time t. So if you're going to find the rate of change of surface area, you're still going to, do these branches here. You're still going to go, okay, the partial of S with respect to L times dl dt plus the partial of S stands for surface area, with respect to width, times dw dt plus the partial of S, surface area, with respect to H, times dH dt. And they already gave you the dl dt, the dwt, and the dH dt. Once again, -1 foot per hour, -2 feet per hour, -1/3 foot per hour, respectively. So you don't have to go and find those guys' derivatives because that's kind of a given. But you do have to get these partials here, the dsdl, the dsdw, and the dsdh. And this is going to be a little bit harder than the volume. Why? Well, because I hope you can see that if you look at this big old sum, if you're going to take the partial of that with respect to L, that means you're going to hold W and H constant. So the derivative of 2WH with respect to L is 0 because there's no L's in there. And then the derivative of 2LH with respect to L is 2H. And the derivative of 2WL with respect to L is 2W. And then you'll multiply that by dl dt. Plus, now you got to go get the partial of surface area with respect to width, W. So you'll hold H and L constant. So you're going to get 2H plus 2L. And you'll multiply that by dw dt. Plus, and then finally, you need to get the partial of the surface area with respect to height. And that means you're going to hold W and L constant. And I get 2W plus 2L, and you'll multiply that by dH dt. And then again, you're just going to plug in those values. So this is going to be 2 times 2 plus 2 times 8 times the negative 1 plus 2 times 2 plus 2 times 9 times negative 2 plus 2 times 8 plus 2 times 9, negative 1/3. And you have to be careful. What are my units? I'm being a little cavalier and not putting all my units in. I get negative 226/3. But what are the units? And yes, you'll get docked if you don't give me correct units. My math lab will dock you also because they want you to pick the correct units. So is it going to be feet cubed per hour again?
No.
Correct. Feet cubed is not going to work. That's volume. What's it going to be for surface area?
Square.
Square feet per hour. And we're done. So the surface area is also shrinking because it's a melting block of ice. And so everything's shrinking. So you guys ready to try one?
Yeah.
Yeah.
Why not? Let's do this. Okay. I'll even give you a multiple choice one. So you and a buddy are going to try a chain rule problem. I'll give you a hint. Use the chain rule. Oh yeah, you're going to need to. So I'm going to put you in breakout rooms right now. So once I open up the breakout rooms, if I can even get my breakout rooms, what the heck? So once you get assigned to a breakout room, go in there. Please turn on your mic also so you can talk to your buddy, so you can actually work together. So that would be nice. And I'll come around and visit in case you get stuck. Okay, I'll see you there.
I'm gonna go make myself some toast or something. I don't know.
Well, welcome back, folks. I just want to point out, here in your Canvas course, there's lots of things that I've put in there that aren't required, but are definitely helpful that I just would like to point out. As you can see, I put lots of videos in here. Some of them are of me, some not. So last week's video has limits, domains, and so this stuff here, showing a limit does not exist along 2 different paths, even though that's in week 5. It should be in week 6. So that's going to be on this week's quiz. I'd recommend that if you still don't get that showing a limit does not exist mini proof, go watch that video. Here in week 6, you got the Zoom video links. By the way, these YouTube videos, what I do every time I do a Zoom recording with you folks, I not only post the Zoom link, I actually download it and then upload it to YouTube. So I have a playlist on YouTube called Professor Rasky's Calculus 3 Spring 21. And so you can find the corresponding YouTube videos for the Zooms, like here. What we did on Monday is already in YouTube. So if you prefer watching it on YouTube, and then we did partial derivatives, I would recommend that you do that. So you're always welcome to look at the YouTube videos, okay? So the other thing I want to point out is last semester, I had to be absent on the day we did partial derivatives. So what I did is in the summertime, I recorded all the partial derivatives lecture, but in pieces. So you don't, if you're tired and you don't want to watch like an hour and a half video of the partial derivatives, you can watch. It's a little more professionally done too, where I didn't make mistakes and go humana. So partial derivatives 1, 2, 3, 4, 5 here, where it says Professor Rasky, that's me. I recorded those myself. And then here we have chain rule for functions of 2 variables. So if you're confused about today's material, I encourage you to go watch some more stuff, or even just to watch it to reinforce. Okay. So the correct answer, for example, 3 here was letter D. And let me just show you the work that I want to see. So on the quiz this weekend, if you want to get full credit, you couldn't just like, oh, I'll just circle the right answer and I won't show anything. No. Step 1, I want to show what is dsdt, like dsdt equals. Don't start doing anything until you tell me. If you skip this crucial step, I will take away points from you. Now, if it helps, draw a little diagram here. The surface area is a function of the radius and the height of a right circular cylinder. Here's a picture of the cylinder here where you've got your height and you've got the radius there. And then the radius and the height are themselves functions of a single variable time t. So you're going to have to first go down this branch and you're going to have to get ds dr, the partial. So look at the letter D's there. You have the melted or the curvy stems times, and then go down this branch, dr dt. This is straight stem since it's a single variable. Plus, then you go down this other branch and take the partial of your surface area with respect to the height times dh dt, times the derivative of height with respect to time. Now, the good news here, just like the last problem, is they're telling you that the radius is increasing at a rate of 9 inches per minute. So this dr dt is 9 inches per minute. They're giving you that. Nice. But the height is decreasing at a rate of -7 inches per minute. So be careful. Decreasing means you have a -7 there. Ooh, okay. Now you need to go get these partials, knowing that the surface area formula was given to you, 2 pi r squared plus 2 pi r h. So if we take the partial of that with respect to r, that means you're going to hold h constant. The derivative of 2 pi r squared with respect to r is easy. That's just 4 pi r, plus the derivative of 2 pi r h with respect to r is 2 pi h. Okay, and that's what I'd want to see on your paper. And then the other partial, dsdh, you're going to take the derivative of 2 pi r squared with respect to h, that's just 0. And then the derivative of 2 pi r h with respect to h is 2 pi r. Now, you get partial credit if you make it this far. Now what? They want the rate of change of surface area for the cylinder when the radius is exactly 12 inches. So everywhere you see the letter R, you'll substitute 12 inches, and the height is 32 inches. You want to substitute 32 for the H, the height. So you're going to have like, sorry, you'll hit 4 pi R, you'll have 4 times pi times 12 plus, and then here you'll have 2 times pi times 32, and then you'll multiply that by 9 plus 2 times pi times 12, and then this is -7, and then you get 840 pi, and because this is surface area changing, it's going to be square inches per minute or inches squared per minute. Same. Okay? Any questions on this? Is this chain rule becoming a little more clear, or sort of? Little
Yeah,
bit? Okay, I don't know. I hope you're getting it more. All right, so I'm going to move on to a different case now. We're going to do case 2. So remember, I started this whole lecture by mentioning there's 2 cases that you need to be aware of in this section. You're going to first have to do functions of a single independent variable, which we're already done with now. We just figured out case 1, we're done. Now the more complicated case, where you have a function of more than one variable, where those variables themselves are functions of more than one variable. So this gets a little messy because you have more than one independent variable. You have more than one variable driving the bus, is how I like to say it. I'm just saying. So we'll start with something somewhat simplistic. Simplistic meaning not too many variables going on. So let's say W is a function of 2 variables, and it's differentiable with respect to those variables. Fantastic. And then X and Y themselves are 2 functions of 2 variables, U and V. So X equals G of U of V, and Y is a function H of U and V. And all of those first partials, dx du, dx dv, dy du, dy dv, all exist. Then you're going to have to worry about 2 partials, the partial of W with respect to U, because that is one of the independent variables, and the partial of W with respect to V. So I'm going to fill in the blanks here. But before I do, I'm going to do the schematic first, because I think it's easier before I actually finish this theorem. I'll show you the Briggs schematic first, and then I'll show you my version, which of course I think is better. You know, not that I'm biased or anything, right? So Briggs, here's your W. W is a function of X and Y, and X itself is a function of U and V, and Y is also a function of U and V. Fine. So I prefer it's similar. So you start with W as a function of X and Y. But these U's and V's that you see down here are really the same U and V. It's not like X has his own personal U and V, which are completely distinct and different from Y's U and V. U and V are just U and V, like this. They're the ones driving the bus. So X is a function of U and V, so we got to draw out 2 branches there. And Y is also a function of U and V. So he's also attached to those guys. So U and V are the independent variables. So they're 2 independent variables, and they're driving the bus. Okay, so now what do we have to do? Well, to get dW du, so the derivative of W with respect to U down here, here's what you're going to do. You got to go down all the right branches. You're going to go the partial of W with respect to X multiplied by the partial of X with respect to U. Plus the partial of W with respect to Y times the partial of Y with respect to U. And we're done getting the partial of W with respect to U. And notice that all of the letter D's here, all of them are for the notation for partials. So all of these D's have that curvy stem to them. So make sure you get comfortable sketching that D, because I'm going to dock you points on a quiz if you can't do that. Now, what about the derivative of W with respect to the other independent variable, V? Here we go. You're still going to get dW dx, so the same dW dx that you got before, times, you got to go down this branch here, dx dv. dx dv. That's a partial, the partial of x with respect to v. Plus, you're still going to go down this branch again. So you're going to dw dy, which you already got from the previous partial. So it's just the same one. Times, and you go down this branch, dy dv, the partial of y with respect to v. And boom, we're done with this theorem. So when you look at these two partials, this one requires 4 partials total. And this one also requires 4 partials total. But the good news is that they have something in common. Both of them have a dw dx. You don't have to get 8 totally different partials. You really only have to get 6 distinct ones because the dw dx's are the same for both and the dw dy's are the same for both. So that's kind of good news. It's still messy. You still got work to do. All right. So let's do some examples where we do the chain rule for this second case. So the next example, they want you to find dw du and dw dv when w is a function of x and y here, where x is a function of u and v, and y is also a function of u and v. Okay? Now, when you do one of these chain rule problems for me on your handwritten work, I'm going to require that you write down what you're doing, like to get credit. Don't go, oh, just look at the theorem, professor. You know, I don't need to write it. No, you're going to write it. So you're going to write down dw du is equal to the partial of w with respect to x times the partial of x with respect to u, plus the partial of w with respect to y times the partial of y with respect to u. So now let's go get all of these things. Okay, in turn. So dw du. We want to take the partial of w with respect to x. So that means hold y constant, where y is a constant. So that means sine of y also looks like a constant multiple. So the derivative of e to the x sine y with respect to x is e to the x sine y. That's nice. And you're going to multiply that with the dx du. So x is equal to u times v squared. You're going to take the partial of that with respect to u. So that means hold v constant, and I get v squared. That's the partial of x with respect to u. Plus, now I'm going to take the partial of w all over again, only this time with respect to y. So we're going to hold x constant, differentiate with respect to y. So the derivative of e to the x sine y with respect to y is e to the x cosine y. Fine. And we're going to multiply that with the derivative of y with respect to u. So we're going to differentiate u squared times v with respect to u. Holding v constant, we have 2uv. Now you're not done. I'll give you like 1 point out of 10 if you get this far. Well, how come? What's wrong with it? You got too many alphabet letters in there. You got x's and y's and u's and v's. It's a hot mess. Well, what do? I only want to see the 2 independent variables in your final result. And the 2 independent variables are u and v. So I want you to rewrite this where I only see u's and v's. So u's and v's only. Well, what do? Well, everywhere you see an x, you're going to replace with uv squared, and everywhere you see a y, you'll replace with u squared v. So it's just a lot of substituting here. And yeah, it's going to get kind of messy. So here, e to the x becomes e to the uv squared times sine of y, but y is u squared v, and then that's still being multiplied by v squared, yuck, plus, and then the e to the x cosine y becomes e to the uv squared times cos of u squared v, and then you're still multiplying that by 2uv. Now, just to let you know tradition, you always want to try and rewrite where you put your algebraic factors in front of any transcendental functions. Exponentials and trig functions are known as transcendental. So it would look prettier so nobody, that's a v, nobody gets confused and thinks that that v squared is part of the argument of your sine. You don't want anybody reading your answer to go, oh, is that part of your cosine or your sine argument? No, it's not. So put those algebraic guys in front. And then it looks pretty and you're done. So there's one of the partials. We're not done. We got to get the other partial because we have two independent variables. Oh man, yeah. I know, I told you this would be messy. So write it down what you're doing next. We want to get dw dv, which is the partial of w with respect to x times the partial of x with respect to v plus the partial of w with respect to y times the partial of y with respect to v. I'm just writing down what it said in the theorem up here. Okay, these are the two partials we're trying to find. Now, the good news is two of these partials we already got from before. We already know what the dw dx was. It was e to the x sine y. And now we just have to worry about what the heck is dx dv. Okay, well, x is uv squared. Take the derivative of that guy with respect to v. So I think I'm going to get 2uv plus, and then we already took the partial of w with respect to y, so I'm just going to copy down what we had last time, e to the x cos y, and then take the derivative of y with respect to v. So the derivative of u squared v with respect to v is u squared. And then you know the drill. Clean this up. Rewrite it so that you only have u's and v's in your final result. So I'm going to totally clean it up. I'll put this algebraic 2uv in front, and then I have e to the uv squared times sine of u squared v plus u squared times e to the uv squared cos of u squared v. Woo! Okay, there's your other partial. What a mess. Now, I'm going to do a problem that Briggs doesn't really have, but I made sure I put a couple into your homework from different textbooks. And this is the kind of stuff I put on quizzes and exams to test if you really are understanding this. It seems like it's complicated and they're trying to trick you, though. So I'll walk you through this one, but know how to do these. Okay, I'm going to read it, and then after we go, oh my God, we're going to figure out the fact that they just gave everybody two names. You know, I don't know about you, but, you know, I have some friends that have nicknames, you know, so like my best friend, her name is Julia. I've known her since I was 5 years old. I never call her Julia. She's got a different name for me. Well, how come? Because when we were kids growing up, we gave each other a weird nickname. I call her Hissel. Ask me some other day where the heck that came from, but I never call her Julia. So in this particular problem, everybody's got two names, so it gets confusing. All right, here we go. Z, I'm going to draw a diagram at the same time. Z is a function f of two variables, x and y. So Z has two names. You can either call him F or Z. It's the same guy. And so we know that Z is a function of X and Y. So here's my little diagram, like so. But then watch out. X is also known as a function G of two variables, S and T. So he's got two variables that he has to worry about like this. And then Y is also known as H, and H is a function of S and T also. So I'm just trying to draw my tree diagram. I'm a tree diagram kind of girl. I love these tree diagrams. That's what Dr. Vallone taught me. Get your tree diagram and you'll be safe. And then it's known that F and G and H are all differentiable, which is a good thing because otherwise we wouldn't be able to use the chain rule. Now, when S is 2 and T is equal to -1, and keep in mind that S and T are the two independent variables driving the bus. So, you know, when S is 2 and T is -1, we have the following values. G evaluated at 2, -1 is 3. So X basically is a 3. But GS, now GS, you have to be careful because GS is the same as the partial of X with respect to S. So that's this right here. That's GS. Evaluated at 2, -1 is equal to 5. And then they're telling us that H evaluated at 2, -1 is 4. So Y is just 4. And then HS, so that's this branch here, because you're taking the derivative of H with respect to S. HS evaluated at the point 2, -1 is 2. And I should probably change colors because it's going to get a little confusing here. HT, what is HT? HT is the same as dy, yeah, dt, that's HT, and they're telling you that's -2, fine. Now they're also telling you that fx, that would be this, is equal to 12, and fy, the partial of f with respect to y, is 7. Okay, now they want us to find dz ds and dz dt. These are both partials at the point when x and y are 3 and 4, respectively. Okay, so it says hint, draw a tree diagram, which I did, and I claim this tree diagram is really going to help me. Because if I start by going, well, dz ds is dz dx times dx ds plus dz dy times dy ds, and then that's when I'm using everybody's first name. But if I give it, different names, this is basically, you could call this df ds, and dz dx is really the same as fx. They're the same because z is also named f. And dx ds is really, since x is g, that's g subscript s, the different notation there, but means the same thing. Dz dy is the same as the partial of f with respect to y, and dy ds is really the partial of h with respect to s. And they gave us all the values. So they said fx was 12, gs was what, 5, fy was 7, and hs was 2. And so this looks like it's going to be 60 plus 14. Final answer, 74. So we got one of the partials. Yay us. Now we got to get the other partial. What about dz dt? So if I use the chain rule, dz dt is, and I'm just going down all these branches here. You first go down dz dx, and then you go down the partial of x with respect to t, that's this branch here, plus then you go down dz dy right here, and then you go down, that's a y, that's pretty terrible y, come on baby, times the partial of y with respect to t. But since everybody has a nickname or a different name, you're really saying df dt, same as dz dt, and dz dx is really fx, and dx dt is really g. Did I say h? This is supposed to be, oh no, that's hs for this. This right here is gt. And then this guy is the partial of f with respect to y, and this is the partial of h with respect to t. And so they told me everything here. So fx is still a 12. And then they told me that the partial of g with respect to t was, I think, -3. And the partial of f with respect to y is still a 7. And then partial of h with respect to t was a -2. And then this is what, -36 minus 14. And I get -50. Okay, so now we got the dz dt. I don't know about units because they didn't give us any units. So no units for this problem. And I'm done. So there you have it. That's one of those weird ones. Okay, final problem before we do implicit differentiation. In your My Math Lab, and I did a screenshot of one of your My Math Lab problems right here. And I had a student last semester, he just couldn't get this. He goes, I don't get this. And he came to my office hours, and I thought we were able to clear it up. And then he seemed to get it. And then the very next exam where I put one of these on there, he choked again. I was like, oh man, I thought we understood it. And he still didn't get it. So if you're a tree diagram person, you should be able to get this. So which one of these 4 choices is the correct tree diagram for what they're telling you here? They want you to get dy dc, where they're telling you y is a function f, and so they're just giving y 2 names, but y is a function of r, s, and t, like this. And so what does that mean? If you're going to draw a tree diagram, let me draw the tree diagram down here. Here's y. Y is a function of r, s, and t, 3 variables. But be careful, r, s, and t are themselves functions of different things. Now, this is where it gets a little messy. And I'm testing you on functions of a single variable versus functions of more than one variable. In other words, you better have correct notation. Do you use straight stem d, or do you use the curvy stem d? R is a function of one variable, C. So what does that mean? That means that this branch right here, the derivative of R would be a straight stem D, because R is a function of a single variable. That's when you use straight stem Ds. Now, what about S and T? Those guys are different creatures. S is a function of two variables, B and C. So S is a function of B and C. So if I go down either of these branches, those would have to be partials, DSDC going down that branch. And then here, this branch would have the partial of S with respect to B. Those letter Ds are melted or curvy. And then the T, he's a function of, three variables, A, B, and C. Oh, dear Lord. Okay, so T, you know, and if I go down this branch, you'd have the partial of T with respect to C, dt dc. This branch would be the partial of T with respect to B. This branch would be the partial of T with respect to A. Okay, here we go. So there's the tree diagram. Now, none of the tree diagrams that are shown here in Briggs match my tree diagram, because I like to show, you know, the three drivers of the bus. So what are we going to do? Look at letter A. We're going to use process of elimination. Letter A can't be it. Why not? Because look at how R looks like it's a function of A, B, and C. And that's not true, because they told us that R is just a function of one guy, one variable. So that can't be right. And then also it looks like they have S here, a function of three variables, A, B, and C. But when they told us the definition of this function, S only was a function of two variables. So this definitely can't be it. All right, let's take a look at letter B. Once again, this can't be right, because we've got R a function of three variables, so that's wrong. And we've got S a function of three variables, so that's wrong. And that can't be. The other thing that would be wrong, now let's just see here, dy dt. Oh, I wanted to mention that this right here is incorrect notation. This should be dy dt. They have it upside down. And then this thing here is wrong notation too. That should be dy dr. And yes, it matters. And then this one here should be dy ds, not upside down. So letter A is wrong for a lot of reasons. But at least letter B, they have the correct notation. dy dr is okay. dy dt, dy ds, that's good. It's just that they had too many branches sticking out of the R and the S. Okay, let's take a look at letter C. I claim letter C is no good either. Even though they do have R a function of one variable, S a function of two, and T a function of three, that's good, but they have this crappy notation again. This should be dy dt. This should be dy ds. This should be dy dr. So that's wrong. So it turns out the only good choice is letter D. It has the correct notation along the branches for the partials, as well as the correct number of branches sticking out of R, S, and T. Now, which one of these correct chain rules below? You see, they want dy dc. So going down mine, you'd first want dy dr, and then you would multiply that by dr dc. Then you would have dy ds, and you'd multiply that by ds dc, plus dy dt multiplied by dt dc. So which one of these choices looks like it would be the correct one?
Part B.
And it turns out letter B. Okay. So you go dy dr times dr dc. If you look at my diagram, that's this times this, plus the second term has you go down dy ds times ds dc. So that's like down here and down here. And then plus the last variable there, dy dt times dt dc. So here's dy dt right here, and then times dt dc. So it's got those three terms. It needs three terms because you have three of your variables that are all a function of C. This letter C, holy guacamole. I mean, that's a hot mess. No way. That's all I'm going to say about letter C. That's a nightmare. Okay, we're officially done with the chain rule. Congratulations. Let's do implicit differentiation. And I'm going to do it in 15 minutes flat. If you have to leave, goodbye. I'm going to finish out today's stuff. Okay? And yes, it's going to be on the quiz Sunday. What if you have a function that's given implicitly? And you did this in Calc 1. They still like to draw tangent lines to the curve and figure out the slope of the tangent line. So for example, if you were to graph that, and I don't know what that graph looks like, but I imagine it's not going to pass the vertical line test. It probably looks like some funky curve. You know, they might want to pick some weird point somewhere like, right there, and then draw a tangent line, and then what's the slope of the tangent line? And what you learned in Calc 1, and this is Calc 1 review, is you take the derivative of both sides with respect to x, keeping in mind that y is a function of x. So you have to use the chain rule, and you probably forgot how to do this, and that's okay, because I'm going to redo it for you right here, because I think you should see it again. Because look, if you have a friend who's asking you some Calc 1 problems, you should know how to tutor them in Calc 1. You're a Calc 1 grad, for crying out loud. You should know how to do this. And this isn't hard. So you're going to take derivatives of both sides with respect to x. We don't know anything about partials. Remember, pretend you're in Calc 1 again. The derivative of y cubed with respect to x back in Calc 1 is, using the chain rule, 3y squared times the derivative of the insides, dy dx, plus the derivative of y squared is 2y, and then using the chain rule times the derivative of the insides, if you will, dy dx, plus this guy, you're going to need the product rule. So the derivative of 4x with respect to x is just 4 times y, plus the derivative of y with respect to x is 1 times dy dx times the other factor, which is 4x. That's the product rule in action. Equals, and now you're going to do the right-hand side. We're still in Calc 1. Well, the derivative of 1 is 0. Fine. The derivative of 5y is 5 times, using the chain rule, dy dx. And then minus the derivative of x squared with respect to x is simply 2x. Now what? Well, you're going to try to solve this mess for dy dx. Well, how come? Because the slope of this tangent line, essentially, to this curve is dy dx, and that's what they want you to go get. So this isn't too hard. When I teach Calc 1, what I tell my Calc 1 students is, hey guys, get all the terms that have dy dx in them on one side of the equation, and then move everybody else to the other side. So you'll notice he's got a dy dx in it, he has a dy dx, and he has a dy dx. So let them stay on this side. This guy doesn't. So I'm going to subtract 4y from both sides. And then this term has a dy dx in it. So let's move him to the left-hand side so he could be with all his buddies. So I'm going to subtract 5 dy dx from both sides of the equation. So now on the right-hand side, you've got the two terms that don't have a factor of dy dx in them. On the left-hand side, you've got 4 dy dx terms. So just factor out a dy dx. And after you factor out that common factor of dy dx, you've got this big old mess, 3y squared plus 2y plus 4x minus 5. And then to solve for dy dx, you're just going to divide both sides of the equation by that humongous expression, 3y squared plus 2y plus 4x minus 5. Okay, and you're done. There's Calc 1. Fine. Well, it turns out there's a really easy way to get this dy dx if you're here in Calc 3. So before I give you the quick and dirty formula, let me derive it for you first. So let's say you have a function w that we're going to call big F, and big F is a function of x and y, and if we replace y with f of x, we can use the chain rule. Well, how come? Because here's what we're doing. We're doing this, x, y, and you're basically saying, well, y is a function of x. You're kind of doing this. So you're going to go, okay, you're going to first go dw dx. This is the, you can kind of say x is a function of x, but it's kind of like that, not really. You're going to go down one branch, fx, times dx dx, like this branch, dx dx, which is really just a 1. And then plus, you're going to go down this other branch, the partial of W, or you're calling him big F also, with respect to Y, times dy dx. There's your chain rule in action. Now, when you rewrite one of these Calc 1 problems and you get everything on one side and 0 on the other, your equation is going to look like your W is equal to a function of two variables equal to 0. So if you take the derivative of both sides of this equation with respect to x, you already know what dw dx is. It's this big old chain rule. And the derivative of the right-hand side, 0, is still 0. So what? Keeping in mind that dx is really just a 1, you're going to solve this for dy dx. So when we do this, you rearrange everything. You first, subtract the fx from both sides. So I get minus fx here. And then you divide both sides by this fy. And you're done. So you do have to know how to do partial derivatives in order to get this dy dx. This is why they don't teach this to Calculus 1 students. They're not ready. You don't want to teach partial derivatives to Calc 1. They're already battling just doing regular derivatives. So here's the official theorem. If you have a function of two variables equals to 0, and it defines y implicitly as a differentiable function of x, dy dx is just negative, don't forget this minus here, big fx over big fy, so long as the denominator is equal 0, of course, that'd be bad. Now, here's the extended version. And yes, all this stuff's going to be on the quiz Sunday. Don't even go there. Yes. What if you have a function of three variables equals 0, and z is an implicit function of x and y? Then your partials, your dz dx and your dz dy, your slopes in the x and y axes directions, basically, can be found. And you're going to do negative fx over fz for your dz dx. And you'll go negative big fy over big fz. And notice how their denominators match. So that's one good thing. The denoms match. Okay, so let's do the Calc 1 problem all over again. Now, please don't show this to your Calc 1 friends, because it's gonna freak them out, and they're not supposed to do it this way anyways. But it is cool beans. So here's the problem all over again. Wow. Get dy dx the Calc 3 way. Aha. Well, step 1 is you have to do a rewrite. You have to get it where everything is on one side and 0 on the other, because you have to get the representation where you have, this is basically what we call a level curve, if you will, because you're setting it equal to 0. This is your big F, who's a function of two variables, x and y. Okay, there's your big F. All right, so what is dy dx? The slope of the tangent line to the curve. You're going to do the opposite of big fx and divide it by big fy. So we're going to go the opposite of the numerator. So let's look at this big mess here. Now you're going to do partials. What is the partial of that with respect to x? So that means you're going to hold y constant. So the derivative of y cubed with respect to x is 0. The derivative of y squared with respect to x is 0. The derivative of 4xy with respect to x is 4y. And the derivative of minus 1 minus 5y with respect to x is 0. And then finally, the derivative of x squared with respect to x is 2x. So we're done with the numerator. And then the denominator, you're going to take a partial with respect to y. Okay, so take the partial of big F again, but this time with respect to y. Okay, the derivative of y cubed with respect to y is 3y squared plus derivative of y squared is 2y plus the derivative of 4xy with respect to y is 4x. And then the derivative of minus 5y with respect to y is minus 5. And I think we're done here. That's it with respect to y. Now compare this answer to the one that we got when we did the problem originally, the Calc 1 method. Are these equivalent? You tell me.
Yep.
Yes.
Yep, they are. But isn't the way we did it a little bit cleaner? Now let's do it for a function of three variables. Now, folks, this is some funky surface, but it's implicit. See, normally when we've been working with surfaces, we've been given explicit form. We've been given the explicit, what do I mean by explicit? Where z, little z is a function f(x, y), and you have all your x's and y's over on one side. You solve it for z. But folks, this function, good luck trying to solve for z. I mean, you maybe could because it's a cubic, but it would just be really hard. But it's going to be some weird surface that doesn't pass the vertical line test. I'd have to graph it with my grapher. But, you know, it'd be some surface here in 3D, which, you know, who knows what the surface would look like. Ooh, like this, you know, something weird. But maybe you could pick a point and you might want to know what is the slope in the positive x direction. What is your dz dx? And, you know, if you were a skier and you wanted to ski on this surface, you know, and then what if you wanted to ski in the positive y direction? What is dz dy? It's a legitimate question and you can get that. But first you have to get everything on one side and 0 on the other. So you first have to get, it doesn't matter which side. So I'm just going to move everything to the left and have 0 on the right. So this is now a level surface of some function of 3 variables. So this right here is your big F, x, y, z. Okay, so dz dx, according to the theorem, is negative fx over fz. So that's going to be, if I take the partial with respect to x for this big old function of 3 variables, what the heck, I'll have a negative way out here. What am I going to get? Whew, I think I'm going to get 6xz for the first term, and that's a 0, that's a 0, and then minus 2xy squared. And then the fz, the denominator, that's going to be taking the derivative with respect to z. I'll get 3x squared plus 6z squared plus 3y. And then the dz dy is going to be a negative fy over fz. Good news, the fz we already did. So let me just copy it down. Same denominator as the dz dx. But now I have to get fy. So if I take the partial with respect to y, I better not forget my negative out front here. I'll put parentheses here. I'm going to have negative 2x squared y plus 3z, I believe. Okay. And if they want you to actually find the slope at a given point, here you would just substitute negative 1, 0, 1 into this guy. And if you evaluate at the point negative 1, 0, 1, I get 2/3. So that means that you're going uphill if you were facing yourself in the positive x-axis direction. I'm done. There's implicit differentiation, Calc 3 style, people. And we're officially done with this section, which is 15.4, I believe. Okay.